This is lecture for random variable part 2.
Hey there, and welcome. You ever wonder how some businesses just know which products are going to be a hit? Or how scientists can sound so confident about their results? Well, a lot of the time, their secret weapon is one of the most powerful tools in all of statistics, probability distributions. And today, we're going to break down exactly what they are and how they help us make sense of a world that's, well, pretty random. So, let's get right to it. How do we actually model and predict the odds of something happening? I mean, whether you talk about a simple coin flip or something way more complex like a product test, there's a way to kind of map out all the possible results. And that, right there, is exactly what a probability distribution does for us. All right, here's the game plan for this explainer. We're going to kick things off with the absolute basics, the building blocks. Then we'll zoom out to the big picture of what distributions are all about. From there, we'll get our hands dirty with some really powerful specific types of distributions and wrap it all up by figuring out how you can pick the perfect one for whatever problem you're trying to solve. Sound good? Let's dive in. Okay, first things first, random variables. It kind of makes sense, right? Before we can talk about how probabilities are distributed, we've got to understand the thing we're actually measuring. And these variables, they are the absolute foundation.
So what is a random variable? It's basically just a quantity whose value is decided by chance. Think about it. The number you get when you roll a die, that's a random variable. Or the number of defective items in a shipment, also a random variable. The key is that the outcome isn't set in stone. It can be different every single time you run the experiment.
Now, these random variables come in two main flavors. On one hand, you've got discrete variables. These are things you can count in whole numbers. Like the number of defective cans in a batch. You can have 0, 1, or 2, but you can't have 1.5 defective cans, right? On the other hand, you have continuous variables. These are things you measure, and they can take on any value in a range, including decimals. A perfect example is the pH value of a liquid. It could be 7.1, 7.15, or anything in between. Okay, so we've got our random variables. Now what do we do with them? How do we organize all that potential randomness? Well, that's exactly where probability distributions step in. They provide the framework, the set of rules that helps us turn what looks like total chaos into something predictable. Now, for any discrete probability distribution to be legit, it has to follow two simple non-negotiable rules. Rule number 1, the probability for any given outcome has to be 0 or greater. You can't have a negative chance of something happening. That just doesn't make sense. Rule number 2, if you add up the probabilities of every single possible outcome, the total has to be exactly 1. No more, no less. It's got to account for 100% of what could happen. Okay. Enough theory. Let's make this concrete with a super classic example. We're going to toss two coins. Our random variable, we'll call it x, is simply the number of heads we get. So what are the possible outcomes here, and what are the odds for each? Think it through. When you toss two coins, there are really only 4 things that can happen, right? You could get 2 heads, a head then a tail then a head, or 2 tails. That's it. And believe it or not, this simple little experiment gives us everything we need to build our very first probability distribution. And boom, here it is laid out in a simple table. So the chance of getting 0 heads, that's the tails outcome, is 1 out of 4, or 0.25. The chance of getting exactly 1 head, which could be heads tails or tails heads, is 2 out of 4, so that's 0.50. And the chance of 2 heads, well, that's just the heads outcome, so that's 1 out of 4 again, or 0.25. And check it out, 0.25 plus 0.50 plus 0.25, it adds up to exactly 1. Our rules hold up. So now that we have this nice little distribution, we can start calculating some really useful stuff. First up is the mean, which you can also think of as the expected value. It's basically the average number of heads we'd expect to get if we did this experiment over and over. As you can see from the calculation, it comes out to 1.0. Then we've got the variance. This tells us how spread out our results are. It's a measure of consistency. The calculation looks a little intense, but all we're really doing is seeing how far, on average, each outcome is from that mean of 1. And for our coin toss, the variance is 0.50. And from the variance, we get something called the standard deviation, often shown with the Greek letter sigma. It's super easy to find. You just take the square root of the variance. So the square root of 0.50 is about 0.71. This number is really powerful because it gives us a standardized way to talk about how much variation or spread we can expect in our results. All right, let's level up and look at our first specialized tool in the probability toolbox. This is the binomial distribution, and it is your absolute go-to for any situation that can be boiled down to two simple outcomes: success or failure. But here's the catch. You can't just use it anywhere. For a situation to be truly binomial, it has to pass a 4-point checklist. First, you need a fixed number of trials. Second, each trial has to have only two possible outcomes. Third, the trials have to be independent of each other. And fourth, the probability of success has to stay the same for every single trial. If you can tick all 4 boxes, you're good to go.
Okay, I know what you're thinking when you see a formula like this. It can look a little intimidating. But don't worry, we're not going to get bogged down in the math. The important thing is just understanding what each piece represents. That px equals x part, that's just the probability of getting exactly x successes. The n is your total number of trials, and the p is the probability of success on any single one of those trials. See? Not so bad when you break it down.
So let's put this formula to work. Imagine you're in a factory, and there's a machine that has a 5% defect rate. You pull a random sample of 10 items off the line. What are the odds that you'll find exactly 2 defective items in that sample? Well, we just plug in the numbers. Our number of trials, n, is 10. The probability of success, or in this case, a defect, p, is 0.05. And the number of defects we're looking for, x, is 2. You pop those into the formula, and it spits out the answer. There's about a 7.5% chance.
But what if the question is a bit broader? Like, what's the probability of finding fewer than 3 defective cans? Well, fewer than 3 means you could have 0 defects, or 1 defect, or 2 defects. So what do? We just use our binomial formula 3 separate times. Once for 0, once for 1, and once for 2. And then we just add those 3 probabilities together to get our final answer.
The binomial is great, but let's be honest, life isn't always a simple success or failure situation. Sometimes you've got multiple possible outcomes, and for that, we need to graduate to a different kind of distribution.
Say hello to the multinomial distribution. You can think of it as the bigger, more flexible cousin of the binomial. It's designed specifically for experiments where you have more than 2 categories. A perfect example is something like a product rating: good, average, or poor. You've got 3 outcomes, so binomial won't work.
And yeah, the formula definitely looks a bit scarier, but I promise the underlying logic is exactly the same as the binomial. It's just calculating the probability of getting a specific number of results in each of your categories. So instead of just x successes, you have an x for each different outcome. Again, don't sweat the formula, just get the big idea. Let's look at a real-world example. Say 5 panelists are tasting a new juice. Based on past data, we know the probability for each rating. So, what are the chances that we get this very specific result? 2 panelists say it's too sour, 2 say it's just right, and 1 lone panelist says it's too sweet. We take all those numbers, plug them into our multinomial formula, and it tells us there's a 13.5% chance of that exact combination happening. So we've covered the heavy hitters, the binomial and multinomial. But there are a few other specialized distributions in the toolbox that are perfect for very specific jobs. And the real skill is learning to recognize the situation and know exactly which tool to grab. Let's put 2 more of these special tools side by side: the geometric and the hypergeometric. The geometric distribution answers a very specific question. How many times do I have to try this before I get my first success? Then there's the hypergeometric. This one is all about sampling without replacement. Think about pulling marbles from a bag and not putting them back. Each time you pull one, the odds change for the next pull. That's when you need the hypergeometric distribution. So at the end of the day, how do you decide which distribution to use? It really all comes down to asking yourself a few key questions about your problem. Are there only 2 outcomes, or are there more? Are your trials independent? And, this is a big one, are you sampling with or without replacement? Once you answer those basic questions, you'll know exactly which tool to grab from your toolbox. You'll be able to model your data and turn all that randomness and uncertainty into real, actionable insight. So, the only question left is, what problem are you going to tackle first?
Thank you. Disclaimer. Artificial intelligence, AI, was used in the development of selected instructional materials in this lesson. The use of AI is intended to enhance clarity, visualization, and learning engagement, while all academic content has been reviewed and guided by the instructor.